Hi, chemists. My name is Kim, and today we are going to be talking about activation energy. Activation energy is generally a part of chemical kinetics, or the study of the rate of chemical reactions, and it helps us to understand why chemical reactions occur and what is necessary for those chemical reactions to occur. Our learning goals for this video are to define activation energy. What does that term actually mean? To explain why providing activation energy is often necessary to begin a chemical reaction in terms of collision theory and bond energy, and to identify examples of sources of activation energy in various reactions, some that you might be familiar with and some that you might not be. Let's get started. This is a lighter. Inside this lighter, there's lighter fluid, probably butane gas or some other carbohydrogen gas that will react with oxygen in the air to release energy and produce carbon dioxide and water. Now, we don't see those two reactants reacting with each other right now, and if I hit the lighter but not with enough force, we won't see any fire. It needs enough force from my hand, enough activation energy being provided in the form of motion, right, the friction, to actually cause us to be able to see fire from the lighter. Otherwise, there would just be matches spontaneously bursting into flames and lighters spontaneously lighting all the time. So that activation energy is a good safety gauge for us in that case. The definition of activation energy in scientific terms is the minimum energy that colliding particles must have in order to undergo a reaction. In real life terms, you can think of it as the energy that needs to get put in to get a reaction to start, right? To get the lighter to start, I need energy from my finger striking the lighter. If I had matches, it would be the energy from my body and the movement of my hand striking the match. Activation energy can be provided in the form of motion, it can be provided in the form of heat, it can be provided in the form of electricity, and it can be provided in the form of radiation, as in radiation from the sun. These are just a few examples of some of the sources of energy for reactions. Let's think about a reaction like the synthesis of water. Two H2 particles react with one O2 particle. So 4 hydrogen atoms total, 2 H2 molecules, are going to react with 1 oxygen molecule to form 2 water molecules in this balanced chemical reaction. Let's think about what might make activation energy necessary. So these 3 molecules are moving around. They're moving because they have a specific type of energy. Do you remember what the name of the energy that describes movement is? So they're moving because they have kinetic energy. And in reality, if these were gases, they would be moving very quickly and randomly all over the place, and they would be moving in their molecules. So these two O atoms would be moving together, these two H atoms, and these two H atoms, because they are chemically bonded together. I'm using magnets here to represent a chemical bond. If I try to separate the molecules, they will come back together, because that's what's holding the bond together, is an attraction that the two atoms have for each other. Specifically, the protons in one atom are attracted to the electrons in another. So let's say we've got the perfect ingredients to get this reaction going. So the O2 molecule is here with the two H2 molecules, but the problem is I can't just get this reaction to happen because I'm gonna have to put some energy in first. In order to make two H2O particles, I'm gonna need to break the bond between these two O atoms, and that's gonna take energy. I have to pull them apart. That's why I'm using magnets here as an analogy. They're attracted to each other. That's what formed the bond. I have to put energy in to pull them apart to get them ready to form a new molecule. And I have to do the same thing with the two H2 atoms. So all of that bond breaking, that took energy. And so if we think about what might cause that to happen, well, imagine that the particles are moving fast enough, they have enough kinetic energy, they're moving fast enough that when they hit each other with such force, like two cars colliding, that they're able to knock each other's atoms hard enough that they separate. And then the bonds can reform in to H2O. And now we've got two H2O molecules here. So again, we needed energy to start this reaction because H2O is two hydrogens bonded to one oxygen atom. I was starting off with hydrogen bonded to hydrogen and oxygen bonded to oxygen. I needed to have enough energy to break apart all of the bonds, and that energy is probably going to come from all of these particles colliding enough times, right? Because probably the first time they collide, it won't be the exact right orientation, or they won't have the exact right amount of energy. But eventually they'll collide in such a way that causes all of the bonds to break between the oxygen molecules and the hydrogen molecules and allow for the new bonds to form. We can actually think about the same idea with the reverse reaction. We're going to be thinking a lot about reverse and forward reactions as we talk about equilibrium, which is related to chemical kinetics often. And so let's also think about the reverse reaction. If I'm starting off with two H2O molecules, do I need activation energy to make that reaction start? You might wonder. So let's think, if we needed activation energy for the forward reaction, do we also need activation energy for the reverse reaction? And the answer is we do, right? These are molecules that are bonded together. No matter what, it is going to take energy to break the bonds. In this case, to break the bonds between O and H and O and H and O and H and O and H. We're going to have to break all those bonds. So this reverse reaction, which is taking two water molecules and turning it into two H2 molecules and an O2 molecule, the reverse reaction is still going to have an activation energy. These two molecules are still going to need to collide with enough energy to make them knock those bonds loose, end up as a bunch of free atoms that can then reform bonds as the products. And for that to happen, we need to reach our activation energy. Let's look at some examples of reactions where we can identify the activation energy specifically that is required to start the reaction. One example that I discussed at the beginning with the lighter is striking a match. The bonds holding the molecules in the match tip together and the bonds holding the O2 molecules together in the air, the oxygen gas molecules together, those bonds need to be broken to allow the reaction to occur. The friction from striking the match against the matchbox creates enough heat to overcome the activation energy of the reaction between the match tip and the oxygen in the air and lead to the match being lit. Once the match is lit, the match itself releases energy in the form of heat. The reaction is exothermic. So the reaction will continue and it will be self-sustaining after an initial input of energy. Another example of activation energy that may be familiar to you is starting a car. The friction from turning the key in the ignition ultimately causes a spark in the car's engine. This overcomes the activation energy required to start the combustion of the fuel in the car with oxygen gas. So what starts as the energy from a person's body and hand turning the key ultimately allows a spark to occur that will overcome the activation energy required to get the fuel and the gas reacting. Another example is cooking food. Cooking food involves a series of chemical reactions depending on the type of cooking you are doing and the specific ingredients involved. But the heat from the stove, which is generated depending on the type of stove, provides the activation energy for the many chemical reactions that occur during cooking. Final example for today is photosynthesis, which occurs in plants. Photosynthesis can occur at many naturally occurring temperatures because radiation from the sun provides the initial activation energy to begin the light reactions of photosynthesis. Now, photosynthesis includes a long series of chemical reactions where the energy released by the prior step powers the next step of the reaction, but radiation from the sun provides the initial activation energy needed. Let's check back in on our learning goals. Hopefully you can define activation energy, both in my words and in your own, and explain why providing activation energy is necessary to start a reaction in terms of collision theory and relating back to bond energy. And finally, hopefully you were able to identify some of the examples that I used of activation energy needed to start various reactions. Next time, we're going to be thinking about how activation energy can be shown on a potential energy diagram. Awesome job today.